Okay, welcome back everybody. We're going to talk about comparing functions now, and so far we've looked at functions in a number of different ways, and those ways are: one, we could look at it in a verbal way, like describing. We have one, and then we have a triangle, and it grows in this way. It increases by 2, and then it increases by 3, and then the next one would increase by 4. So this is a verbal way to describe the function. We've talked about a graphic way to describe the function, and we can plot points, or we can use a bar chart, or anything like that. So this is one way to describe it. Another way is the numeric way, and we make a table of values. We say in the first step there's 1 piece, in the second step there's 3, in the third step there's 6, and so on. And then finally is a symbolic. In the symbolic, all the way down here, we can say for some given number, we plug in that number and then we get out a result. So this is kind of the high-powered direction we want to go, is to be able to predict with certainty what the result will be given a certain input. So these are the different ways that we can describe a function. And then when we compare functions, we want to compare the same thing to the same thing. So is this function the same as this function? Well, no, it's not. They have different descriptions, right? This one increases by 2 and 3. We call this a triangle of different sizes, right? This one starts with 3, and then it increases by 2 and goes to 5, and then increases by 2 again and goes to 7. So then we can look at the numeric, and here we have 1, 1, 2, 3, 3, 6, right? Our different steps. And over here it was 1, 3, 2, 5. Step 3 had 7. In the numeric, we can compare the different steps and see how it's changing. What's the rate of change of the function? So this one changes. It goes from 1 to 3. So the difference between 3 and 1 is 2. So we're adding 2. And the difference between 3 and 6 is 3. So we're going to add 3, right? So the rate of change is not constant. It's not changing by the same amount each time. So this we can say it's not linear, right? This one, it goes from 3 to 5. So it's changing by 2. And this one's going from 5 to 7. So it's also changing by 2. So this is changing by a constant amount. So this one is linear. And then when you look at the graph, you see that it has a constant rate of change. So this one's going up by 2 over 1, up by 2 over 1. And we have a constant slope that looks like that. Now this one does not change by a constant rate. So it goes up by 2 and then up by 3. And then it would go by 4. So plus 3 plus 2. And I imagine that going backwards another step, it will go up by 1, right? So I could kind of plot this point right here as 0, 0, right? Because if we had no triangles, we'd have no squares, right? Or if we had 1 less 2, if we had 1 less 2 here, what will we have? Right, if we went down 2, we'd actually be at 1, right? So I think the 0 spot here would actually be 1. I'd have, see here I'm taking away 2, if I go backwards, taking away 2, take away 2, take away 2, I would end up at 1, right? So actually this one, the point 0, comma 1 would be probably on that graph. Alright, so now looking at the symbolic for these two, this one, as I talked about before, it's the triangle function. It's 1/2 base times height, where the base is the number, right? So this one's 2, and this one's 3. And then you can almost imagine like the rectangle kind of looks like this. That would make it cut in half. See, and the rectangle would look like this. So this rectangle would be n by n plus 1. So 3, and this one's by 4, and then divide by 2, cut it in half, you get 6, right? So this is n and n plus 1 divided by 2. So that is this symbolic representation of this function. The linear function, though, so what do we see here? We see n is to the first power, and we have a constant. What is this 1? Where does 1 come in to the graph? Or where does this 1 come into the numeric? Actually, our other point was 0, 1, right? So when n is equal to 0, what happens? 0 times anything is just 0, and it goes away, right? So I'm just left with 1. So this constant term, we call this the constant term, which is just a number by itself with no n attached to it. This constant term is what we call the y-intercept, so where it crosses the y-axis. And then the 2, how does this come in? This is the linear term. And it's what gives us the slope. So each time we're adding 2, right? What happens if you repeatedly add the same number? So I took 1 plus 2 plus 2 plus 2 plus 2. All of these plus 2's could just be simplified into saying, well, it's just 2 times the number of 2's, right? 2 times the number of 2's. So that's what this actually comes out. It's 2 times the number of 2's. So at the first position we had 1 2, so it was 3. The second position we had 2 2's, so it was 2 times 2, which is 4, plus 1 is 5, and so on, right? 3 2's, 3 times 2 is 6, plus 1 more is 7. So this is how the symbolic representation of the function is derived in comparing functions that are of a linear type. So they have n to the first power, and it's be times the slope, plus just the constant term, and that's your y-intercept. So we're going to talk about this a little bit further in the next module, but I just wanted to kind of give a little bit of background of where this comes from before we get on to that. So now, comparing functions, if a function is the same, it should be the same, the graph should be the same, or the symbolic should be the same, or the numeric should be the same, or the verbal description should be the same. So we want to compare apples to apples, so let's take a look at this. So is this graph a representation of is the function that represents this graph the same as the function that represents this table? So to do that, I would have to either make a table of values for this and see if it matches up, or I can make a graph of this and see if it matches up. But let's do both. So what is this? So in the first slot, we have, let's see, 1. What is my value? 1, 2, 3, 4. And then at 2, it's 3. And it looks like it's halfway between 3 and 4, so I'm going to say 3.5. And then at 3, it is 3. And at 4, it's 2.5. And at 5, it is 2. So I could tell you right now that these two are not the same, right? This is a linear function, but it's not this linear function. Now, so not the same. These are both linear though, because I can tell this one's going down plus a negative 1, right? Or it's going down 1, down 1, down 1. So it's a constant rate of change. So I know that's a line. Let's go ahead and graph it though. So what is this? The first point is at 5. So first point is at 5. The second point is at 4. The third point is at 3. And 2. And it probably goes on like that. So looks like it's going like this. So if I were to go back to the 0 point, what would it be? It would be 1 more, right? Because it's, if I'm going in this direction, instead of subtracting 1, I'm adding 1, right? 2 to 3, 4 to 5, 5 to 6, right? So I imagine 0 would be 6. And what happens if I go back here 1 more? It looks like each time I'm going up by a half, right? 2 to a half, 2.5, 2.5 to 3, 3 to 3.5. So it'd be 4.5, right, at 0. So I could tell you the symbolic would be, let's see, each time it is going down by a half, right? So my linear term, it's going down by half, so minus a half times n, and then when it's 0, I'm at 4.5, so plus 4.5. So that would be my symbolic representation of that. And the symbolic representation of this is each time I'm going down by 1, right? So I'm going down by 1, so it'll be minus 1n. And when n is 0, I have plus 6, right? And you might see it like this, minus 1 times n, or you might see minus n plus 6, and drop that 1, because that's not really necessary. People will drop that all the time. Okay, so there's your graph, your numeric, and your symbolic. Here is your numeric, graph, and symbolic, and we can just compare them and see that these are not the same functions. Okay, so you'll have some exercises on this, and you're going to develop your own tables from the graph and your own graph from the table, and also try to look at the symbolic while we're at it.